In this video, we're going to talk about the unit circle and some of its properties. So let's first talk about what a unit circle is. A unit circle is a circle that has a radius of 1 unit that is centered at the origin in the Cartesian or xy plane. So that means that at any given point from the center, the length of the radius is 1. So if we were to draw our triangle, that means that the hypotenuse of any right triangle that I draw, any reference triangle that I draw, is going to be 1. And that helps us figure out our x and our y. So any point on the outside is going to have a hypotenuse of 1 with the reference triangle, and this x length is going to be this point out here, and the y height is going to be the y point out here. So that's how we get those points on the outside of the circle, or the coordinates on the outside of the circle. And we can actually derive them using right triangle trigonometry with the sine, cosine, and tangent ratios that we know. Hence why any point on the outside of the circle that's derived from any of those trig ratios is like saying cosine of theta, comma, sine of theta as its ordered pair, because if that's theta and this is x and that's y, it's going to give you those two coordinates. All right, so here's a look at our classic unit circle. Now, before you get overwhelmed with this, let's talk about how you would read this. So if this is the origin, right, our y-axis, our x-axis, we know that the radius is going to be 1. We know that this point out here is 1, 0, 0, 1, -1, 0, and 0, -1. And going out here, it gives you the degrees of the angle that it's referring to, and also the value of that angle in radians. And then if you were to draw the triangle, the point on the outside of the circle is given to you in cosine, comma, sine, which is actually a nice little cheat sheet to find the cosine and sine of that angle. So let's take a look at the domain and range of those 6 trig functions. Now, they all have all real numbers in common, but sine and cosine have a domain that is all the real numbers with no restrictions. It's when we get into combining those two or inverting those two that we have some restrictions. So if I look at tangent, the domain of tan, it's all real numbers with the exception of odd multiples of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2. It's going to have an asymptote at every pi over 2. Cosecant and secant have all real numbers except integer multiples of pi. So your -2 pi, -1 pi, pi, 2 pi, etc. for both of those. Those are also going to have limitations there because some of those sine and cosine values, when you plug them in, are 0, and when you divide by 0, that's undefined and creates asymptote. And cotangent, well, if tangent is restricted for every odd multiple of pi over 2, it makes sense that cotan would also have restrictions, but that is every integer multiple of pi. So range is also going to be a limitation. It's going to have all real numbers except for certain things. Sine and cosine, all real numbers, but only from -1 to 1 inclusive, meaning it includes -1 and 1. Tangent has all real numbers, and then cosecant and secant, all real numbers greater than or equal to 1 or less than or equal to -1, so it doesn't have that middle range. And then cotan is all real numbers, just like its inverse function. And here's a quick look as to why certain restrictions or asymptotes exist. So like we were talking about with tan at first, it's undefined at 90 and 270, which is pi over 2, 3 pi over 2. It'd also be at 5 pi over 2, etc. And our sine and cosine, where it's pi over 2 and then our pi over here, that is going to give us 0, and when we invert it, we can't divide by 0, so that's why the inverse of sine and cosine have those restrictions. So the unit circle creates sine and cosine, and from there it creates tangent, and we can also find its inverses. And all of those functions are what we call periodic functions, which means that its graph has a cycle that it completes, and it repeats over a certain period on a graph. So when we look at sine and cosine and tangent and its inverses, they also have what we call periodic properties. So what that means is however long it takes for sine and cosine and tan to complete one cycle, it's what we call a period. So that means that it will repeat. So the same information that happens in the first period will happen in the second, the third, etc. So what you're looking at right now is that if I have sine and whatever angle I have, if I add 2 pi to it, because 2 pi is sine's period, it pumps out the same value of sine of theta. Same thing for cosine, same thing for cosecant and secant, because those two are inverses. Now, it's different for tangent, and you can probably guess that the period of tangent is pi, and the period of cotan is also pi. And if we take a look at it using our unit circle and our reference triangles, if I have theta either with sine or cosine, and let's say it's this angle right here, I have to go around 360 or 2 pi to recreate that same ratio. But for tan and cotan, this angle, we only have to travel 180 or pi radians to achieve the same result. So let's take a look at an example. So let's use periodic properties to find the exact value of sine 420. I know 420 is greater than 360, so I can say, so what I need to do is find the difference between 420 degrees and 360 degrees. And so if I know the difference is 60, that means that sine of 420 is the same as sine of 60 plus 360, or 2 pi. And I know from the previous slide that that's the same as saying sine of 60, because the period is 2 pi. If I add it on, it's the same value. And sine of 60 degrees is radical 3 over 2. So if the unit circle creates sine and cosine are periodic functions, the even-odd property of functions applies to these trig ratios and these trig functions as well. So recall that if I'm given some function, if I plug in the negative x into f of x, if I get out negative f of x, so if I get out the entire function negated, that function is odd. And if I get out the same function plugging in negative x, that function is even. So the same works for our trig functions. So if I take a look at my even-odd properties, here I see that sine, cosecant, tan, and cotan are odd because they give you the negative value of the entire function, whereas cosine is even because it gives you the same value back. Now let's take a look at a quick example. Let's say I'm given sine of negative 45 degrees. I know that that's going to be the same as negative sine of positive 45 degrees, given that here, and that's going to give me a negative square root of 2 over 2. That's going to do it for this video. Thanks for watching.